Alright, we're going to try and explain the quick drop valve in a practical application for you today. And that is to say there's a valve attached right to the piston end of the cylinder that in the right situation will allow oil to go from the rod straight over to the piston side and increase production. And we're going to increase production by reducing cycle times. I have a pressure differential cylinder. I have an actuator over here with a blade on it. And I've got a valve that starts out normally closed oil flow. So it's closed physically by a spring creating force this way to push over this plunger. And if I have enough pressure on this side, I will overcome that and open that. But it's going to start out normally closed until the right situation happens. And then if it opens, we'll allow oil to go to the piston side. That's our goal. First off, there's a few things involved in this quick drop valve. There's a few requirements. One, it definitely senses upstream to open that valve. However, how I've drawn this initially is the blade is up in the air. So if the blade's up in the air, then logically it's going to require some kind of pressure in order to hold that blade up in the air. And let's just give this an example of maybe 2000 psi. Well, if it takes 2000 psi, then I have 2000 psi working this way to open this plunger, and I really only have a 50-pound spring. That would say logically that the 2000 psi should win against the 50-pound spring, and that would shuttle open, and the blade would fall to the ground even when I want to try and hold the blade in the air. Well, that's not going to work, so we need to add something to this. So what I'm going to add is an orifice on the rod side, and on this side of the orifice I'm going to add another dotted line, and that is to say another sense line. So if this is in hold, which means for all practical purposes the oil flow is blocked, then there's no flow across this orifice. As long as there's no flow across the orifice, the pressure will equalize on either side of the orifice. It's like taking a water bottle and squeezing it down when it's half empty, and the pressure will be the same on either side in a confined space. So as long as there's no flow here, this pressure will be equal, which means I now have 2000 psi on this side of the orifice as well as that side of the orifice. So what's actually holding this valve closed now is 2000 psi working this way, and I will have the same 2000 psi working this way plus my spring, which really means that I have a force of 2000, and if I put a 50-pound spring on it, 2050 psi. Well, 2050 on one side versus 2000, pretty sure this is going to win, and that valve will stay closed. And this is how the quick drop valve can actually hold a load up in the air. And it's all due to more than one sense line and this orifice. I could lower it down slowly and hold the oil back so that this would always remain with pressure, or I can fully function this DCV. And if I fully function this DCV, then really whatever pressure I have here on the tank, which should be atmospheric, and we'll just call it 0, whatever pressure I have there on the tank is going to be the same as no restriction through the DCV, then this should be 0. And if this is 0, then I take away the force that was helping the spring. And I still have the blade up in the air, so I need pressure in order to hold that blade up. And the pressure is 2000. So 2000 on one side versus 0 plus my spring. My spring is only 50 versus 2000 working this way. Pretty sure this is going to win now and physically shuttle this over. Boom. Instantly. and that blade will instantly go right down to, physically the blade will drop right down to the ground instantly. And that's not so bad. So the blade drops instantly to the ground. That is to say that it did not have to wait for the pump to now fill the cavity that would have occurred even to open that up. There's nothing to hold it back, and the blade could physically cavitate the cylinder. So I would still have to wait for the pump to catch up to whatever the actuator, the cylinder, drew out for oil and cavitated it. I don't have to wait for that cylinder anymore. The cylinder is full of oil right now. When it hits the ground, then I don't need any more pressure here to hold it up. There's nothing. I don't need to hold that blade up anymore, so there's no pressure in here, which means this drops to zero, thereabouts. So now this is what really goes on. I'm at zero over here, and I still have a 50-pound spring. So my valve physically now closes. And theoretically, then I can create some kind of down pressure on this. And the only other scenario on that is we have to understand that every orifice creates a pressure drop, or we have to remember that every orifice creates a pressure drop. And because there's a pressure drop here, if I was to fully function this and try and go as fast as possible, well, the reality of it is it may create some kind of pressure on this side to reopen that valve. And that is to say, that's great, but I got resistance now. I'm on the ground. I have resistance. So if I'm going to actually move anything, then I have to create some kind of pressure up here. And if I have to create pressure up here, then why don't I take that pressure and physically hydraulically lock that valve closed so that it can't open up. So I'll always have this pressure plus the spring, which is more than anything that would happen from this minor resistance on this orifice. And if I want to go and lift the blade up, then here's what it needs to do. It needs to, one, any pressure that was up here, that's going to be gone because that connects the tank. That's okay. And then I have spring force, which is trying to hold that closed, plus whatever I need to create here. So what's really going on is whatever force I need to create there, well, say it's back to my 2000 psi to hold that blade up in the air, well then I'm definitely going to have 2000 psi plus the spring on this side versus the 2000 on the other side, with the relative understanding that really every orifice creates a pressure drop, and maybe my pressure drop is 50 psi. So if I took the original 2000 over here originally, I would maybe be 2000. I could write better. If I was to originally take the 2000 over here, then the reality of it is I'm back to 2050 psi plus the spring is still enough to overcome the 2000 to keep this closed. So I can physically raise it up in the air. And if I put it in hold, then this will equalize to 2000, but I still have enough force to keep this closed, and I will be able to hold this blade wherever I raise it up in the air, up to a certain point. Great. The blade is off the ground. I'll just bring it up all the way. Well, not all the way, but fair ways. Just like we do back home on the farm. Anyway, when I bring it up in the air part way, then and put it into hold, then I still have, as soon as I go to hold, then it's pressure. These two will equalize because there's no flow across the orifice, and the spring will still hold that closed. Again, if I was to go down slowly, slowly restricting the oil flow here, then I could have a controlled lowering. However, if I want to increase production, then by all means, put it into quick drop. And whatever pressure is there, compared to no restriction, 0, 2,000. Instantly, this shuttle's open, boom, the blade falls to the ground. And all I know is you gotta have a hook in the water if you expect to catch a fish.